So welcome to this morning session. So our first speaker this morning is Professor David Weld, and he will tell us about, this will be the part 2 of his talk on cold atoms, quantum simulations, and driven quasicrystals. So over to you.
Okay, thanks so much. Excuse me, let me just share my...
Share your screen.
Yes.
Okay, that's good. That's good. Yeah.
Looks good.
Thank you.
Okay, great. Well, good morning, everyone. Thanks so much for coming to part 2 of my talk. Again, I really would appreciate it if people would ask questions. I thought that actually went really well yesterday, so I'm very happy to stop at any point and take questions. So yes, this is part 2 of the talk begun yesterday, and I adjusted it a little bit since yesterday. So now what I plan to talk about is some topics that are really, I think, pretty on point for this program. I'll talk about periodically kicked, spatially quasi-periodic matter, beginning by discussing anomalous localization in a kicked quasicrystal, and then moving on to discuss in a related system, coherent control of a localization quantum phase transition using phasonic driving. And then at the end, partly in response to an email I got from an audience member, I'll say a little bit about a new experiment that we're building and a new field, which is emerging right now, which could be called quantum interactive matter or quantum interactive dynamics. I'll just give my 2 cents on that. There's no results in that third part of the talk, but there hopefully will be plenty of results in the first 2 parts. Okay, so mostly what I plan to cover is the results of some recent research in my group, and this concerns the exploration of localization. And I'm not going to talk about all of this work, but there's a variety of things that we've been doing recently in this area in my group. The ones that I've marked here in red, I'm not going to talk about today. So we had some work on what I would call many-body delocalization, so the effects of interactions on dynamical localization in quantum-kicked rotors. That was a collaboration with Viktor Galitsky and related closely to work that was done also by Deep Gupta group. Excuse me 1 second. Can I get you something? Okay. So the second reference here is related. It's also a study of a fundamental phenomenon that occurs in Anderson localization called the quantum boomerang effect. That was a collaboration with Tommaso Macri, and it was something that we were just fortunate shortly after it was theoretically predicted to realize that our experiment was able to probe. And then the third red reference here is a study of quantum thermodynamic engines, so cyclic processes with quantum degenerate working fluids, looking at how energy can be transferred in that kind of circumstance and with what efficiency, and whether quantum degeneracy makes a difference. And that's work we just recently put on the archive. But I'm not going to talk about any of that stuff. What I want to talk about instead today is first some work on anomalous localization in a kicked quasicrystal, which is currently on the archive and under review. And that's exploring a new phase diagram that we're very excited about. Then secondly, as I said, a technique for controlling a localization phase transition using phasonic driving. That work is not even on the archive yet, but should be pretty soon. And then in the end, if there's time, I'll talk a little bit about this new direction that I mentioned of quantum interactive matter, quantum interactive dynamics, and tell you a little bit about an experiment we're building to probe that area. Okay, so diving into the first part of this second part of the talk, the first topic is anomalous localization in a kicked quasicrystal. So let me give, I think localization is probably something that's a sub-theme of this program, but I'll just sort of say a few words about it quickly. So it's been known for quite a long time, since at least the work of Phil Anderson shown here, that you can drive a quantum phase transition between a metal and an insulator just by adding disorder to a system. And it's been known basically as long that this disorder doesn't need to be true disorder, that quasi-periodic disorder will also drive a metal insulator phase transition. And this is due to the work of Aubry and Andre, and which is closely related to the work of Harper that's related to integer quantum Hall systems. And these are well-cited papers. This is a topic that a lot of ink has been spilled on already. So today, what I want to do is try to say a few new things about the topic of localization. And the main experimental tool that I'll use is the one that we discussed from a little bit of an unusual perspective yesterday. It's quantum gases, and in particular, it's driven quantum gases, which is the main area of interest of my research group. So let's dive a little more specifically into the Hamiltonian, which is going to be relevant to the majority of this talk. So this is the Aubry-Andre-Harper model. One way to look at this Hamiltonian is as a prototype of real space localization phase transitions. So the Hamiltonian is very simple. It just has two terms. It has a hopping term here. So this destroys a particle at one site and creates it at the neighboring site that has an amplitude J. Looks like a kinetic energy term in a tight binding model. And then the second term you might call disorder, although it's not actually disordered at all. It's quasi-periodic. And it is a chemical potential modulation, which is incommensurate with the underlying lattice. So this lambda tells you the strength of this additional perturbing potential. The n is just a number operator, which tells you that this is a chemical potential term. And then this cosine of 2 pi I alpha plus phi is incommensurate with period ratio alpha to the underlying tight binding lattice. So this is a model that you can think of this in a couple different ways. You can think of this as a model of a one-dimensional quasi-crystal. This is a system that has no disorder but no translation symmetry. That's a good working definition of a quasi-crystal. You can look at this, and this is relevant for our experimental realization, as something that's realized by just overlapping two lattices. If you overlap a red lattice and a blue lattice, and their ratio of their wavelengths is their wavelengths are incommensurate with each other, then you'll end up with a lattice that, treated as a tight binding model, is going to give you a Hamiltonian that looks like this. And finally, this model, as those of you who have studied the Harper model will be aware, is relevant to the physics of two-dimensional electron gases in high magnetic fields. In other words, to integer quantum Hall systems. So the very first topological insulators that people started to study have an energy spectrum, which is to say the integer quantum Hall states have an energy spectrum which is identical to the energy spectrum of this one-dimensional Hamiltonian. So what I want to talk about for the first part of the talk is a slight generalization of this Aubry-Andre-Harper model, and it's the kicked Aubry-Andre-Harper model. So the only thing that's added here is this term in red, which says that the incommensurate chemical potential perturbation, whose strength is described by lambda, isn't just on all the time, but is only kicked on at certain times during the dynamics, with period big T between the kicks. And what's shown here is delta function kicks. So what this model describes is almost always just a plain old tight binding lattice with just tunneling, the simplest possible model, which will give you an ordinary band structure. But then every once in a while, you turn on this quasi-periodic perturbation. And so the first question this motivates one to ask is whether the type of localization that we generally expect in the Aubry-Andre model, which I didn't maybe say it already, but it supports an Anderson-like metal insulator phase transition at finite values of lambda. Can that occur in a system which is almost always periodic, except during these delta function kicks? So that's the first question we want to experimentally investigate. Let me pause here and see if there's any questions about the underlying model, the nature of the model, or the interest of the model, because this is something that we're going to be discussing for the majority of the talk, these one-dimensional quasi-periodic models. Any questions or comments from the audience?
No, it doesn't look like it.
Okay. Please feel free to jump in. Or is there a question? I saw you guys are very small for me.
Yeah, a simple question. So do you have any intuition what happens in these quasi-periodic models when the parameter alpha becomes very small?
Hmm.
And whether
Good
that's
question.
experimentally feasible?
It's like a very small magnetic field in an integer quantum Hall system. It's experimentally feasible. You could use a very long wavelength lattice, or which you would realize by overlapping beams at an angle rather than doing retroreflected lattice configuration. It's going to look like, as alpha gets very small, it's going to start to look like regions of periodic crystals that are very slowly modulated. So to probe the physics of very small alpha, I think you'll need a larger and larger sample. It's like, yeah, in the same sense that, you know, in weaker and weaker magnetic fields, the radius of the Landau orbitals is going to get larger and larger. I think that a similar kind of thing is happening at small alpha. The alpha that is typically taken to be of interest for this model is around the golden ratio, 1.618. And actually we use a different, somewhat smaller value here, but you know, not tiny, not too far from 1.
Okay, thanks.
Sure. One interesting thing is that the physics of this model is fundamentally different depending on whether alpha is rational or irrational. And that's weird because, you know, you can make very tiny changes to a number and change it from being rational to irrational. But if alpha is a rational number, this does not support an insulating state at all. It just has a band structure. It has a large unit cell. And if alpha becomes irrational, then it supports the insulator. So there's an interesting sort of very delicate hierarchy depending on alpha, which is related to the Hofstadter butterfly and maybe familiar in the context of quantum Hall physics to some of you. Yeah, great question. Okay. So just to say, another way to look at this model, I haven't talked much about kicked rotors in these lectures, but it is a topic of interest for my group. And another way to look at this model is just as a kicked rotor. So we have the same kind of pulsed cosine term that a kicked rotor has, but now instead of an ordinary free space kinetic energy, we have a band structure. So it's like a kicked rotor with a different dispersion relation. That's an equivalently reasonable way to look at this model, which connects it to some of our other work, for example, on the quantum boomerang effect or the many-body dynamical delocalization. Okay, so what is the phase diagram like of this model? This has been explored only theoretically before our experiments, and it can be, in certain regimes, understood pretty straightforwardly. So in the regime of small t, and remember big T is this parameter in the Hamiltonian, it's the period of the kicks. So in the regime of small t, which is to say very rapid kicking, unsurprisingly, the model can be effectively time averaged. And it time averages to the static Aubrey-Andre-Harper model, which, as we already said, supports a metal insulator phase transition. And as I didn't say, but as many of you may be aware, this metal insulator phase transition is actually protected by a duality. It occurs at exactly lambda equals 2J. And that physics, including the duality, comes through to the kicked Aubrey-Andre-Harper model in the regime of small t. So a good way to draw the phase diagram, and these are the axes that we're going to use for most of the phase diagrams I show in this talk, is to put lambda, sorry I made it capital here, but it's still just the strength of the quasi-disorder on the x-axis, and to put the kick period t on the y-axis for fixed, kick duration. And in this case, in this high-frequency regime, you see the system has a phase transition between a metal or a superfluid-like state and an insulator-like state at a lambda, which depends on the value of t. So you see this line, which has slope 2, which is pinned to 2 by this duality, and the metal and the insulator live on either side of it. And right at the phase transition, there's a critical state, which is very interesting and has fractal character, but only exists at one that one line of measure zero in the phase diagram. More interesting things happen as you increase the period t. So this is where things get really exciting and interesting in this model, is where t starts to be large, and in particular where t starts to be on the order of the tunneling time, which is inversely proportional to the term j. So if you think about what happens in a model that's kicked with a period that's comparable to the tunneling time, well, it means atoms can tunnel in between kicks, maybe a few times, maybe just once. And what that gives rise to is some effective long-range interactions in the model, where between kicks, you can have atoms that move over more than one lattice site. And that creates off-diagonal matrix elements in an effective model, which gives rise to something which is sometimes called a generalized Aubrey-Andre-Harper model, which has terms beyond the first off-diagonal. And it's known as one of the potentially interesting consequences of such long-range hopping, that it can stabilize critical multifractal states, not only at the phase transition, but elsewhere in the phase diagram. And so what's shown here is actually not just cartoons, but the results of calculations in the kicked Aubrey-Andre-Harper model, just kind of laying out what these different states look like. So a localized state looks like this. It's exponentially localized. Where the density of the wave function is non-zero is on a region with sort of compact support. So it just looks like a spike on these axes. An extended state looks like it's spread out over the whole lattice with some, bumpy spikes, because this is still a quasi-periodic model. That's what's shown up here. And a fractal state has different character. In particular, it has the fractal feature of self-similarity. So what you see here is little bits of this wave function zoomed in 100 times and 10,000 times, and you can see the same patterns repeating and repeating. This is one of the signatures that the wave function in this regime is a fractal. And this kicked Aubrey-Andre-Harper model supports all three kinds of wave functions: localized, extended, and fractal or multifractal. So as I said, things get much more interesting. So I showed you the high frequency phase diagram here, which is cool, but kind of trivial. Things get much more interesting as you go to the high T limit. And this has been explored theoretically already a little while ago in the two works cited at the lower right of this slide, and also explored by our collaborators Tarun Grover and Peter Liu, who are pictured at the lower left of this slide. So what you're seeing here again on the left is a phase diagram with kick period on the y-axis and kick strength or quasi-disorder strength on the x-axis. And you see that the phase diagram is much richer. The original duality protected phase transition line is this dashed line, and you see that's still valid at small values of t and lambda, but you see all this other structure where you see metallic states away from that line and insulating states away from that line. And you can see that the phase diagram is much richer. So I want to point out,
David, can I ask a question? What is the color bar? Is that the inverse participation ratio? Or
oh,
what is
sorry,
being
yeah.
plotted there?
I'm going to show a couple different color bars. In this case, this is a little, you could plot IPR. That would be a good thing. And we do have some phase diagrams with that on it. In this case, it's something a little more experimentally relevant. And let me explain what it is. Good question. So these sigmas are sort of second moments of a density distribution. And what this is telling you is how much the second moment of a density distribution has expanded throughout some wait time. So that's a little bit of maybe an odd way to diagnose localization, but it's one that's very well connected to experiments. Because what we do to actually probe this model is we put some tightly confined bunch of Bose condensed atoms into the lattice, and then we wait some time while kicking the lattice in the appropriate way, and we see how that distribution spreads out. So what this color bar is telling us is by what factor did the second moment of that distribution increase in some more or less arbitrarily selected wait time.
So is
And
this
it turned out,
sorry,
go ahead.
So in the static Aubrey-Andre model, one of the key features is that the multifractality at the transition occurs throughout the spectrum. Right? So every single wave function is fractal. But in this kicked version, do you develop mobility edges? I mean, so when you're loading the atoms into states, are they the low energy states? Where are they populating in the spectrum?
Good question. So we can't necessarily select that. We just sort of load them into whatever states have spatial overlap with the initial moderately tightly confined BEC. It does turn out to be the case that at a generic point in this phase diagram, you might have, you will have some localized states, some delocalized states, and some multifractal states. And so you can load a mixture of those.
I see. Okay, thank you.
Yeah, really, really good questions. And a little bit relevant to the right-hand graph shown here. So this is picking out the fraction of the states that are fractal, that have some fractal dimension different from 0 or 1. And for the Aubry-André model, as you just said, if you look at this dashed line, you can see that there's basically no fractal states anywhere except right at the transition. The x-axis here is distance from the transition, basically. But at the transition, you have 100% fractal states. So that's what it means that this little dashed line is sort of a delta function around 0. For the kicked Aubry-André-Harper model with lambda equals 1, so that's way down here at the lower left in the high frequency kicking regime, the same thing is true. Basically, in this region of the phase diagram, you only have fractal states right at the phase transition. The cool thing is, if you go into the high T regime, high T and high lambda, getting near the phase transition for lambda equals 5, T equals 2.5, say, that's around here, then you see that actually the percentage of fractal states remains sizable, even rather far away from the transition, and is non-monotonic with distance from the transition. So that's actually the second one of the two interesting features that I wanted to point out here, is that there's an extended multifractal regime in this regime of high T and high lambda. You can kind of see that from the purple line here. The first thing I wanted to point out is that there's regions of this phase diagram where you have something that we would call reentrant delocalization. So that means, imagine going to like 1.5, T equals 1.5, and moving horizontally on this phase diagram. You'll drive a transition from a metal to an insulator, back to a metal, back to an insulator, and back to a metal, and so on and so forth. So there's a somewhat exotic regime where increasing the strength of the disorder actually delocalizes the system and vice versa. And so these are general features of actually a very rich and beautiful phase diagram that's not entirely captured by this plot. If you did plot it with IPR, it makes it more manifest that there remains this beautiful duality, even in the high T regime. And there's a lot of other interesting features of this phase diagram, including some serious subtleties about the approach to the thermodynamic limit. But unless people have asked questions about it, I probably won't go into too much of detail about that, because what I want to talk about is how we probe the interesting features of this phase diagram experimentally. Okay, so but let me pause here and see if there's any other questions about what we're shooting for before I get into the experimental realization. No questions? I can't necessarily see if you guys are preparing to ask a question because you're all very small on my screen. Okay, well, I'll press on and await any questions at any time. So how do we experimentally probe this model? Well, I would say in basically the maximally simple way. So we have a quantum gas. In this case, it's strontium-84, and it's tightly localized in an optical trap. And we drop that into an extended static lattice, which has an incommensurate lattice applied over the top of it. And that second lattice is just pulsed on every once in a while. And the observable is just the spread in position space. So it's like a transport experiment. We just put the atoms in at one point, and there's a sizable number of them, about 100,000. It's not just one or two atoms. And then we watch how they spread out in position space as a function of time. And actually, the images along the bottom of this slide are pictures of a quantum gas of strontium that's sort of spreading out in a lattice like this. And if you just wait for different hold times, you can take a sequence of pictures like this and reveal a lot of details about the dynamics of spreading and thus about localization in the system. So can we use this simple setup to observe the localization phase diagram as we vary the kick period T and the quasi-disorder strength lambda? So we can, and here's the first look at some of that data. So in the upper left, you have, again, some of these sort of stroboscopic movies as a function of hold time, where you see if you're in an area where the system is superfluid or metallic, you see the atoms are spreading out as you wait for longer and longer times, up to about 2 seconds. Whereas if you go to a region of the phase diagram that's localized, you can see that not much changes as a function of hold time. So the difference between these two types of evolution pictures are going to be the thing that we use to diagnose localization. And you can be more quantitative about that. You can plot the second moment of the distribution as a function of hold time and fit it to various power laws and learn about the exponents that characterize transport at different points on the phase diagram. So if you do that for a whole bunch of different kick periods and a whole bunch of different kick strengths, you can experimentally map out a phase diagram like the ones I was showing on earlier slides. And so that's what's been done here in this graph on the right. This is experimental data. So there are some good things and bad things about this data. One of the good things is that we observe, as predicted, a period-dependent localization transition. So the system goes from being delocalized to localized, and that transition happens at a value of the disorder strength, which depends on the kick period. And the slope is actually as expected. This is a slope of 2, which is expected by the duality of the model. So that's nice. What's not so nice is at the upper right, all these cross-hatched areas are areas where the data failed cuts intended to diagnose loss and heating. So the atoms are all either kicked out or heated up to be extremely high temperatures, to the point where we couldn't really tell if the system was localized or delocalized. And what this is really a signature of is the breakdown of the techniques of Floquet engineering that we're using to realize this model. And they're breaking down exactly where things should start to get interesting at higher values of T and lambda. And in particular, this breakdown is quite bad because if you look at the values on the axis here, these are the same units of T that I was using before. It's in units of the tunneling time. So we're only getting up to about 1% of the tunneling time and some equivalent lambda that gets us near the phase transition. And already the Floquet engineering is breaking down. So this experiment, as shown here, is utterly unable to probe the regime where the interesting stuff is predicted to happen.
David, can I ask another question? So what seems interesting is that actually you have, gray blocks going sort of all the way down, separating the delocalized and localized phases. And there's some expectation in electron systems that multifractality can strongly enhance interactions. So is that possibly a signature of additional heating close to the transition, even further down along the phase diagram?
I wouldn't rule that out. That's not something that we've investigated in detail, but we actually have just revived this experiment and are taking more data on it now. So that sounds like something we should think about. But I will say, like the gray cross-hatching here, it may not come across too well on the screen. It only appears inside the yellow circle. The gray areas down here at the lower left are not actually discarded data, but just in the color map, like intermediate around 25. So this is a bipolar color map that's supposed to sort of show transitions well. But that's quite interesting. And there are interactions, by the way, in this model, not in the Hamiltonian, but the atoms can see each other. They interact about as strongly as rubidium atoms. And that's something that we have been interested in probing. And I don't have data about that, but maybe I'll just say now, since you asked. We've tried this at different interaction strengths, achieved by just using different atom numbers. And we see about the same phase diagram. So we don't think that we're in a regime where interaction is controlling at least the gross features of the phase diagram. Yeah, good question. But yeah, basically this is a sort of sad story because we see a lot of loss and heating happening, and it happens like way before anything really cool should happen in the model. So what are we to do?
There's one more question.
Question, do you hear me?
Yes.
So regarding the interactions, Like, can we assume then the interactions remain static in the system? Because when you're implementing the Aubrey-Andre type potential, right? Like, you're also changing essentially the lattice depth, and then this might also affect, you know, the Vanier function. So can we assume that the interactions are static, or are they also in principle driven by the kicks?
I think you can assume that they're static during the course of a single kick. The kicks are quite rapid compared to the transport dynamics of the atoms for most of the values we use. But they're not static over the course of a whole experiment. If you look at these data up here in panel A, you can see that the atoms are spreading out significantly during the course of an experiment, and that's giving rise to a much reduced density. So interactions just, you know, in a mean field sense are going to be weaker at the end of that experiment than at the beginning. But I don't expect they should change significantly over the course of a single kick, which is just you know, a few microseconds. It's a relatively small amount of time for the atoms to move around.
Thanks.
Sure, good question. Okay, so what do we do about this problem identified with the crosshatched area? So this motivated us to try to look into the origins and possible solutions of this heating. And basically, panel A is a little bit complicated, but it sort of shows that we understand what the problem is here. So if you vary the kick period, finally, you start to increase it and see what happens when things go wrong, and you plot the decay rate of the atoms as a function of that. Well, the square boxes are the data, and the purple line is a model, assuming that all that's going on is we're driving transitions to higher bands. So, you know, real atoms in the real world have kinetic energy. Even electrons have kinetic energy in a crystal. It's something that, as an experimentalist, I always want to kind of take seriously, although it's ignored in any tight binding model. So, so what's happening here is at particular values of the kick period, the atoms are able to absorb energy from the kicking resonantly and make a transition to a higher band. And that breaks our model, right? Because our tight binding model has no higher bands. So as the atoms get heated up there, they're just going to tunnel much faster. They're going to leave the region of interest or get heated up, and we won't actually be realizing the kicked Aubrey-Andre-Harper model. And so the match between experiment and theory in this panel A is basically showing you that that's what's going on. We spent a long time diagnosing this, and it turns out to be the case that what's happening is our kicks are heating the atoms up into higher bands. And panel B sort of shows why this is the case. The purple shaded areas are the frequency regions of concern for driving transitions to higher bands, the first band, the second band, and the third band, according to the labels. And the blue power spectrum is the power spectrum of a square kicking pulse with the indicated frequency. So you can see that we have like a lot of frequency overlap with dangerous areas. We're going to be driving transition to higher bands, heating the atoms out of the ground band, breaking our tight binding model. So this is sort of our Floquet engineering technique breaking down. The solution is indicated also in panel B, which shows that if you don't use square pulses to kick, but instead either Gaussian pulses or pulses that have been intentionally filtered to reduce the noise in the areas of concern, just digitally filtered, then you can significantly minimize the overlap between the purple areas of concern and the power spectrum of the drive. And I won't go into all the detail of panels C, D, and E here, but I'll say that what they show is that this, what you might call apodized Floquet engineering, which simply means shaping the kicking pulses to minimize the power spectrum at interband energies, works actually really surprisingly well, and allows us to reduce the heating in many cases by orders of magnitude, depending a little bit on the kick period and the length of the kicking pulses themselves. So maybe just to give an example, the lower right data here show for a tau, a kick time of 100 microseconds. If you don't do apodization and you look at the atoms as a function of hold time, which moves vertical here, the atoms are instantly boiled away. This is a signature of extreme heating. The atoms leave, you don't even see them anymore after about a third of a second. Whereas if you do the same power kick with an apodized or Gaussian pulse, the atoms hang around and you can diagnose the fact that the system is in an insulating state. So this is a a technique which is very pedestrian in some ways. This is a direct relative of apodization in RF engineering or optical engineering. If any of you are familiar with those fields, that's where this word comes from, apodization. But it's I would say has surprising practical efficacy. This was a technique we kind of played around with to try to make things a little better, and it made things a lot better. So what it allowed us to do actually was open up a much larger area of the phase map. And in particular, it was actually 100,000 times larger area of this phase diagram we could probe simply using these apodized Floquet engineering pulses. So now my cheapo animation consists of just stepping through slides, but what I'm doing is starting with that original phase diagram I showed you and zooming it down to show our new phase diagram on the same scale. And now you see, this is also experimental data using the apodized pulses. And what we can see is that now we can get the kick period up to 4 tunneling times without suffering heating that's too bad. There's still a bit of heating you can see from these cross-hatched areas. We understand that that's from driving resonances in the transverse modes of the lattice. But the heating that completely destroys the phase diagram is basically totally gone. This apodization technique let us explore this much larger, interesting area of the phase diagram. And we see indeed some interesting features. So I want to just point out a couple of those. The first thing we see is reentrant delocalization. So if you go around 1.5 or 2 kick period here and move horizontally, there's a regime where increasing the kicking strength drives a transition to an insulating state, then back to a metallic state, as you hopefully, depending on the projector, can see from this salmon-colored peninsula here, and then back to an insulating state, and so on and so forth. So the reentrant delocalization is a feature that we can probe in this larger phase diagram, and it matches reasonably well the theoretical expectations for the model. Actually, this is an old theory. We have new plots which match the experiment better and are also a little bit better justified. The second thing to say here, and this is something that we have more data on recently, but I'm showing here some old and very well characterized data, is that you can measure the transport exponents. So not only how wide did it get, but what was the functional form of the width increase. And it turns out that that's a possible way to diagnose multifractality. And those exponents do indeed suggest that if you draw a line across the phase transition, like the line shown here, they suggest that there's an extended multifractal regime. Not only at the phase transition do we see anomalous exponents, but actually for a wide range around that phase transition. So these are two of the interesting features of the model that we identified theoretically at the outset: reentrant delocalization and extended multifractality. And by exploring this much wider phase diagram, we actually are able to see experimental signatures of both of them. So this is the main result of this first part of the talk, is that we were able to measure the phase diagram of the kicked Aubrey-Andre-Harper model. There's an interesting way, which I won't go into, to think about this as a model of a driven integer quantum Hall system. Maybe a practical note here is that in any case, there's other reasons that this phase diagram is of interest, and there's a lot of beautiful physics here that could be explored. So we're excited to have the first experimental access to it. As a practical note, we think this apodized Floquet engineering, which is an extremely simple technique, was actually a really key enabling technique in letting us see this phase diagram at all. So it was only because we developed and used that technique that we were able to observe the reentrant localization and delocalization and the first indications of this multifractal regime. So that's what I want to say about the kicked Aubrey-Andre-Harper model, although we do have more data on this and we're studying a bit more in the lab right now. Let me pause there briefly and see if there's any questions about that section of the talk before I move on to a related but distinct topic of phasonic control of localization.
I have a question. In your parameters, T and lambda, where's H bar buried in there? Is it in T? Like if I made the system more or less quantum, which direction would I go?
That's interesting. I don't know how to make it less quantum, but let me pull back up the the Hamiltonian here. I mean, I guess it's in the, I mean, these are raising and lowering operators. I'm not sure how I would take a classical limit of this model. Does anybody else see the answer to that? I feel like I might be missing something obvious.
I think certainly the kicked rotor. Oh, we got a suggestion that it's in alpha, but yeah, I mean, certainly the kicked rotor has a classical limit, right? It's some map. There's a classical map you can put it onto, but okay, I guess, I mean, if you made things more quantum, I might expect it to delocalize.
That's very interesting. In the kicked rotor, there is a well-defined thing you can do that makes the system more or less quantum, and we do have some data on that, but not in this talk. In this case, the kinetic energy term here, this is a tunneling term.
Yeah, that's got to be
So-
quantum. Yeah.
So this is already kind of intrinsically quantum. I don't immediately see how to kind of take a classical limit of this unless it's to replace this by a free space dispersion relation, in which case you would identically have a kicked rotor, actually.
Mhm.
So yeah, it's a really interesting question, but I guess as far as I know, this is like a quantum mechanical type binding model. And it's not obvious to me how to make it super classical. I don't think it's by varying alpha. That varies an effective magnetic field. But I mean, even if lambda was 0 and he didn't have the second term at all, this would be a tight binding model of a simple lattice, and it would have a band structure.
Yeah, that's
just
the
like
the
an-
kinetic energy, sure. Yeah.
Yeah, an ordinary quantum mechanical model of a metal. Yeah, great question. Sorry not to have a crisper answer.
I had just another question. So could you vary the wavelength of these bichromatic ones? Could you sort of kick, in that case, you could keep the intensity constant. You'll realize some version of a kicked AH, but not exactly this. But then
Interesting.
heating is not probably that big an issue there, right? If you
So make
periodically
make alpha a function of time.
something like that, or in the basically make it commensurate incommensurate in a
Yeah,
kick
very
manner.
interesting. We want to do this. I don't think we can do it over the course of a single experiment, but we bought a very fancy laser to do this, which is a titanium sapphire laser that can be tuned across a broad range. I don't think we can vary it over the course of a single experiment, although that's a very interesting idea. It would correspond to a rapidly and hugely varying magnetic field in the integer quantum Hall model. But what we can do is try one alpha and then another alpha and then another alpha and sweep out a parameter range like that. And what that we think will actually let us do is directly image the Hofstadter butterfly, because the energy spectrum of this model is the Hofstadter butterfly. If you vary alpha and do spectroscopy, you should see that famous fractal energy spectrum emerge. So that's something we're very excited about. The idea of doing it dynamically, we haven't thought about much, although I think it's a very interesting idea. Yeah, great questions. Any other questions about this first part? I may have to sort of speed through the second part, but that's okay. I think it's much better to have discussion.
Hello. Oh, that's working.
Yes, I hear.
I just wanted to ask a question about sort of touching on the duality thing. So I think one way of looking at these Harper problems is that you can think of that dispersion, the tight binding part, as being like a cosine P in momentum space.
Exactly.
So you've got the two terms like cosine P, cosine X, basically, and
Mhm.
so is it possible to explore this kind of localization physics in momentum space, where you would load everything into a plane wave and watch it delocalize, and you'd see this phase diagram flipped or something like that?
Yes, exactly. I mean, that's exactly the duality, as you say, is between position and momentum, and the Hamiltonian looks like kind of the same if you flip the role of those two. And yes, you can explore it in momentum space, and actually that's what we did in our quantum boomerang and kicked rotor experiments. So in that case, the localization actually occurs in momentum space, not in position space.
Okay, great.
And yeah, so this is very possible, and it's even relevant to experiments.
Okay. Fantastic.
The thing that wasn't so obvious to me, and I'm not sure it's been published before, but people, when you tell them, they kind of say, yeah, that makes sense, is that duality is 100% preserved in the kicked model as well. The duality is very famous for the Aubrey-Andre model itself, but in the kicked model, it's still there. So you still should have everything symmetrical around this line. Yeah, thank you guys for the great questions. Okay, so let me say a couple things. This is a shorter topic about some unpublished work that we are also sort of finishing up right now, also in a one-dimensional quasi-crystal, but now trying to coherently control the localization phase transition. So now I'll be talking about something else. Instead of adding a kicking term to this model, we're going to go back to the static Aubrey-Andre-Harper model, which just has hopping and incommensurate quasi-disorder. And we're going to look at this additional term phi, which is just a phase on that incommensurate perturbation. And in particular, what we're going to look at is what happens if you make this parameter, which I'll call a phasonic parameter, because it corresponds to the phazon degree of freedom of a quasi-crystal. What happens if you make that parameter time dependent? So this is the red is the new ingredient here. We have an ordinary Aubrey-Andre-Harper model, except the phase of the secondary lattice is now a function of time. So at high frequency, we explored this a little while ago already, and you actually see something pretty interesting, which I'll just flash up without discussing too much. So if you shake the model with what I'll call dipolar driving, which is not a phasonic drive, but just shake everything back and forth. This is a bit like applying an oscillating electric field to the model. Then you see the ground band fraction responds only at a particular frequency, which is the frequency of the interband transition. So this is no surprise. This is just doing band spectroscopy on this model by applying an electric field. And it's a quasi-crystal, but it basically still has a band structure because the secondary lattice is rather weak. So you see a simple response. In the case of phasonic driving, as indicated by this cartoon, where you just drag one lattice with respect to the other, you see a drastically different response. And this was very puzzling to us when we first saw it, and we worked together with Egidius Anasimovas and Andre Eckhart, my theory collaborators who are shown here, to understand this. And it's basically a non-perturbative high harmonic response that's a consequence of phasonic driving. And it's pretty cool, but it's not what I want to talk about. What I actually want to talk about is what happens if you modulate this phasonic parameter sort of slowly. And what we want, the reason that we tried to do this was we thought that if you have an Aubrey-Andre model and you stir around the incommensurate disorder, it should kind of destroy the localization. It should heat everything up, scramble the effect of the localization, and make the system back into a hot metal. This was basically our expectation, at least. If you do this very, very slowly, we know that it drives a topological pump. But I'm talking about doing it at some intermediate frequency regime, and it kind of seems like it should just scramble the whole system. And indeed, if you do this, you can take pictures of the atoms and see that something like this does happen. So these pictures are taken for increasing values of the pseudo disorder strength. And if you don't have phasonic driving, you see the localization phase transition in the narrowing of the atomic distributions as you move from left to right. And if you do add phasonic shaking, like the one I just showed in this cartoon here, then you see that the phase transition, the localization phase transition appears to be suppressed. So that seems to make sense. But then if you keep turning up a knob, something strange happens. So if we drive the phasons at larger and larger amplitude, we do indeed see that localization is destroyed, the system delocalizes. But then at an even higher amplitude, it localizes again. At a still higher amplitude, it delocalizes again. Then it localizes again, and so on and so forth. So we see a very surprising to us, non-monotonic response to the intensity of a phasonic drive to a localized Aubrey-Andre model. So what is going on here? If you plot what's going on, just to give a more quantitative view of it, so I'm looking now, plotting here on the y-axis, the width, which is again some proxy for how delocalized the state is. It's how much the atoms have spread out after some time. if you plot that as a function of phasonic shaking amplitude in nanometers, you see that there are these peaks where it delocalizes, relocalizes, delocalizes, and relocalizes again. And the physics doesn't even really depend on the drive frequency. I'm plotting 3 different drive frequencies here, and you see that they all do more or less the same thing. And along the top, you can see pictures of the atoms delocalizing and relocalizing and so on and so forth as a function of the phasonic drive amplitude. So the clue that helped us figure out what was going on here is the observation that those peaks of delocalization actually occur at the zeros of a J0 Bessel function. So this is this may be familiar to some of you as something called a Jacobi-Angé expansion. So in the description of our Hamiltonian, we have a term that looks like the cosine of 2k times x minus a sine omega t. That a sine omega t is the oscillating phase of the secondary lattice. And that can be expanded. And the first term in that expansion just has an ordinary cosine of 2kx multiplied by a J0 Bessel function whose argument has to do with the amplitude of the phasonic drive. So what's happening here is actually a dynamical renormalization of the quasi-disorder strength lambda, where it gets multiplied by a Bessel function and thus acquires a value which oscillates as you increase the driving amplitude. And the cool thing about this is it gives us a tool for coherently controlling localization. So I put this reference on here, which is a long ago but quite famous reference, doing something similar, not with phasonic localization, but with like shaking the whole lattice back and forth. In that case, the quantity that was renormalized was the tunneling. In this case, the quantity that's renormalized is actually the disorder strength. So if you plot an appropriately normalized inverse spreading measure as a function of shaking amplitude, and then plot a Bessel function, you can see that we think we understand this pretty well. This is not a fit. This is just the absolute value of a Bessel function. And it fits the data rather well. So a kind of cool thing about this is that in this second lobe, we actually expected the disorder strength is negative. We can't resolve its sign. So I've plotted the absolute value of J0 here. But we do think that we should have in fact flipped the effective sign of the quasi-disorder. And it's also possible to flip the effective sign of J using a similar technique of phase modulation. So the thing that we're exploring now is whether we can use this to reverse the direction of time in our Hamiltonian by changing, inverting the sign of all elements in the Hamiltonian. And another thing to say about this is it actually serves as a very convenient practical tool for controlling a localization phase transition. So I won't go over all the curves on this plot, but just focus your eyes on the yellow triangles. In this case, we had a system that was localized. Then we turned on phasonic driving, the system delocalized. Then when we turned off the driving, it relocalized again. So clearly what was going on was not some sort of heating, which destroyed localization, but actually a coherent knob that allowed us to switch back and forth across this quantum phase transition in a way that was reversible using this phasonic driving. So that's what I wanted to say about coherent control of localization. I have a few slides left on a new experiment in quantum interactive matter, but maybe rather than rush through that, let me pause here first with, I guess, 5 minutes to go in the hour and ask if there's any questions about the coherent control of localization. Okay, so hearing none, maybe I'll just proceed with the last little bit of the talk. So now we're done with the results. I just want to show you a little bit about an experiment we're building now and some future ideas that I think are going to be important in our field. So let me spend 3 minutes on that and then see if any further questions have arisen. So we're building a new experiment. And I'm not going to go into details on the experiment too much, except to say that it involves potassium Bose condensates in optical tweezers. So everyone and their cousin is building an optical tweezer experiment now. There's nothing very unique about this because it's a very exciting new tool in our field. The thing that is a little bit unique about this apparatus that we're building is that we're not going to have individual atoms in the tweezer sites, but rather small Bose condensates. And we think this is going to give us an interesting platform for reconfigurable synthetic quantum matter. So this is a design of the experiment laid out at the lower right. Maybe I won't even talk too much about this. We have some Feshbach coils. We can control the interactions among the atoms using Rydberg interactions, but also using Feshbach interactions. And the apparatus is nice and small. So we can bake it in an oven. We've built it. This is a picture of the nice clean design and the messy reality on the right. And actually the little glowing ball in the middle there is a nice cold gas of potassium at about 30 microkelvin sitting inside the apparatus now. So this is something that my graduate students are just putting together now, and it's kind of starting to work. What do we want to do with this? These are my last couple slides, and I just want to introduce what I think is kind of an exciting new direction for our field. So traditional quantum condensed matter physics, which is a lot of what we try to study with optical lattice tools, is a very powerful and rich arena for understanding structured quantum systems. So in some sense, you can think that if you take quantum mechanics with wave-like particles and you add a periodic lattice, you get all the richness of band structure, topological insulators, semiconductors, what have you. If you do the same thing and add a lattice in time, you get the richness of Floquet matter. And that's some of the things I've been telling you about already in this talk. A paradigm shift that moves beyond both of those is to expand your conception of the system to include the observer as an essential piece of the quantum system that's evolving and being measured. And this is, in a sense, what I view as the simplest definition of this new field of quantum interactive matter. So looked at with respect to Bloch matter and Floquet matter, I made these little cartoons to kind of talk about what one of the ways to think about this new field. So a Bloch system, these are all little space-time diagrams with time moving up and space moving to the right. So, a Bloch waves in a crystal are understood as being due to spatial periodicity. If you add in time periodicity, you get some new richness that we've described in this talk. If you add in measurement and just occasionally measure the system as it's evolving, you're in a regime that you might call xenomatter. This is the regime of the measurement-induced phase transition, which I'll say something about on the next slide, and which many of you have heard about. A totally unexplored area, largely unexplored anyway, is what happens if you add measurement in a space-time system like this, take the results of that measurement and feed it back to future system parameters. This is the regime that I would refer to as interactive matter. So the theoretical context here is the context of monitored dynamics. It's been known for a few years now that just observing a quantum system can give rise to new states of matter. And I won't go over all these references. These are just the references by my two colleagues, Sagar and Matthew, pictured at the lower right. There are also many other excellent theorists working on this around the world. This is a hot topic in condensed matter physics right now. But it's coming to be rather well understood that measurement can drive interesting phase transitions. Feedback is something that's been less well explored, except in the particular specific case of quantum error correction. So let me just close by saying that this new apparatus we're building, we hope it's going to be a tool of exploration for this new regime of quantum interactive dynamics. Some of the tools that are enabled by this apparatus are going to give rise to capabilities that let us explore monitored dynamics, single shot feedback, and ultimately continuous feedback and measurements, which I would say is the full and really wide open regime of quantum interactive dynamics. Okay, I know I'm basically out of time, so let me flash up my conclusions. I told you about measuring the phase diagram of the Kicht-Aubrey-Andre-Harper model. I told you about non-equilibrium coherent control of a localization phase transition with phasonic driving. And then I babbled briefly about a new direction that I'm very excited about, which is called quantum interactive matter, and an apparatus that we're building to study it. Let me close by thanking my research group pictured here, all of our collaborators, the funding agencies who support this work, and all of you for your attention.
Thank you.
And I know that we're out of time, but I'd be happy to take questions for any amount of time that the organizers deem wise.
Can you hear me? Oh, yes. Could you repeat again what you can do or what you saw with multifractality?
Sure. We don't have the ability to image the wave functions on a fine enough scale to observe multifractality. I think doing this experiment in a quantum gas microscope would be very interesting. Then you could actually image the fractality of the wave functions. What we can do is measure transport exponents, and that's an indirect probe of multifractality. And what we can also do is actually pretty good theory on this phase diagram at this point. And it's a very uncontroversial theoretical statement that multifractal wave functions exist across a broad swath of parameter space in this model. The question is, what impact does that have on the experiments that we can do? The main impact is that it gives rise to anomalous transport exponents. I mean, the most measurable impact, I would say. And so that's the data we show here, is that there are anomalous transport exponents hovering around a value of 0.5 in a wide range of the phase diagram in a place that's consistent with an expectation of multifractal wave functions. The theory at this time has much better resolution for diagnosing the intricate patterns of multifractality in this phase diagram, which are certainly there. The experiments are just able to suggest it at this moment, I would say, but I think future experiments probing this in more detail are certainly possible.
How do you picture in your head multifractality? I mean, I can picture a fractal and Mandelbrot, and I keep going through all these, but now you have multiple.
Yeah,
what is
yeah.
it?
There's a hierarchy of fractal
Fractals,
structures,
oh.
and the other thing to say is that
And it's a continuous hierarchy or it's discrete?
that's a good question. I'm not sure is the answer. So let me not say something I'm not sure about. But it is the case that at any point on this phase diagram, there exist all three kinds of wave functions. And I guess I didn't put up a graph of that, but we have some good theoretical maps of that. You can see the mobility edge and the fractal wave functions open up and close down as you move through the phase diagram in a beautiful way.
Thank you.
Yeah, so in one of your future goals slide, you kind of showed something like quantum thermodynamic engines or something like that.
Mhm.
But that would kind of require to controllably realize some notion of a bath. But do you have an idea of how to do that?
Yes, we would do that with multiple samples of atoms. So we've thought a lot about making real heat engines. Right now, we've made a thermodynamic engine where you don't actually need a bath, but to make a heat engine, you do need a bath. And the basic idea would be to maintain large reservoirs of hot and cold atoms, and then have another trap that you could controllably couple to those two reservoirs while changing its internal control parameters. I think in that way, it would be relatively straightforward to realize something that looked like an Otto cycle or a Carnot cycle, but using a quantum degenerate working fluid. That would be interesting. And then even more interesting would be to study the effects of entanglement on multiple copies of an engine like that. I think these are actually the original motivation for our tweezer apparatus before we got excited about this quantum interactive dynamics area. And I still think there's some pretty interesting possibilities there. We did, in advance of finishing this apparatus, do some initial quantum thermodynamic engine work on our lithium experiment, which is on the archive now.
Thanks.
But without a bath.
Okay. Hi. So I wanted to know this, that for the phasonic control that you're doing, you're changing phi continuously, right?
Mm-hmm.
So what if you made that a kicked thing that, you have different phis at different kicks, right? Is there something interesting that can appear there?
Yeah, very interesting. So do the phasonic control, but in the kicked.
In the kicked manner, yes.
Yes. We've done this, and I really thought it would just heat everything like crazy, but it doesn't. It does the same sort of reentrant delocalization. The Bessel function renormalized disorder basically works just the same in the kicked model as it does in the static model, to my surprise. But yeah, it basically more or less does the same thing.
Thank you.
Thank you guys so much for all the great questions and for coming to the talk.
Thank you.
Sorry again to miss it in person, but please enjoy the rest of the day.